Hello students, this is Professor Urvish Mewada, HOD Electrical Department, Sri Swaminarayan Institute of Technology, Bhat Gandhinagar. I am the subject matter of Industrial Instrumentation subject, which is in the 7th semester, and GTU subject code is 2170913. Before we start the new chapter, in last three lectures we studied about the introduction and classifications of the transducer and basic requirements of the transducer. Now this is our fourth lecture, uh, and in fourth lecture we are starting with the new chapter, that is chapter number 2, strain gauge. So in the strain gauge, we start with the topic number 1, that is introduction. So first of all we'll understand what is stress and what is strain, and then after we'll see in detail the working function of the strain gauge. So generally strain gauge means strain means what, we are means pulling something in xy direction, means we are applying the force, mechanical force, and so as the due to the elastic limit of any particular substance, it will get stretched, and due to the stretching of that material, the dimension of that material will change, and as the dimension of that material will change, its as dimension, or we can say shape changes, its resistance will change. So here we are using Hooke's law for the better understanding of the strain gauge. So Hooke's law generally states that the Young's modulus means elasticity of any material is proportional to the longitudinal stress applied, to the inversely proportional to the longitudinal strain applied, means it is a ratio of stress over strain. So stress is basically defined with S over here, and epsilon defines the strain. Now here one substance is, means shape of the substance is drawn. You can see the length of the substance was L, and when we apply the force from both the sides, means in this direction, means longitudinal lateral strain. So due to the strain, the length of this object will change from L plus delta L, and so as the this is the width, means the width of this element was D, so that will be D minus delta D, means that will become due to the stress or the force applied, the shape of this object will change, means this is the D, means diameter, or we can say width of the object is changes from D to delta D, and the length will change from L to delta L. So when any body or means having length L, means it is elongated with the stress, so the length will become delta L, and due to the application of the force, the dimension means this D will also change, and D will become D to delta D. So the strain generated in this particular direction is called the lateral strain, because it is in the one direction, means you can see that this is the x, suppose this is the x plane, then this is called the lateral direction. Now here one more law is applicable, that is the Poisson, means Poisson shows that the ratio between a lateral strain, means this is the lateral strain, and longitudinal strain. So due to this longitudinal strain, means both are constant for a material, means dimension will change from both the direction, means vertical as well as the horizontal. So it is called the Poisson's ratio, and it is denoted by V. So we'll use this Poisson's ratio also in this derivation, means relation between stress and strain. Now as we seen the relation between stress and strain, so in the next slide is the change in the dimension, or we can say diameter, delta D by D, means change in the dimension, diameter to the original diameter. It is the ratio of this delta D by D to change in length to the original length. So from this theoretical analysis, we can say that Poisson's ratio for the solid must be lie between 0.5. So for most of the material it is 0.3. So therefore for the isotropic 3D solid, means the material which is having we can say dimension in all the planes x, y and z. So that's why it is called isotropic 3D solid material. So that will with a generated in x direction, and we can write the following equation like suppose x direction, so change in the length or dimension in the x direction to the original dimension in the x direction. So as we explained the Hooke's law, E is equal to S by epsilon. So here epsilon, here we are making it as a subject, means strain. So strain is equal to, in the x direction will become stress in the x direction to the Young's modulus. Now for the y direction, so it is minus delta y to y. So for y, the strain will become epsilon y is equal to minus v into ex is equal to minus v sx by e. Here v is the Poisson's ratio, so we are applying this Poisson's ratio over here. And for delta z, it is minus delta z by z. So epsilon z is equal to minus v ex to the minus v sx by e. So from these three equation we can say if the stress are generated simultaneously, means one by one along other two directions, so here the equation will become equation of ex will become sx by e minus v sy by e. If you solve this the equation will become like this, and minus v sz by e. So here we are considering all the planes x, y and z. Similarly for the ey, the equation will become sy by e minus v sx by e minus v sz by e. Similarly for z, so the equation will become sz by e minus v sx by e minus v sy by e. So these three are the equations for the stress which are generated, means sorry, due to the stress which are generated simultaneously, the equation of the strain. Now again we are continuing this derivation. So we are rewriting the above equations means of the previous slide. So if we make the subject sx, then this the equation will become like this: e into epsilon x plus v into sy plus v into sz. And similarly for, we can write the equation for sy and sz. So here we are considering in two-dimensional system sz is equal to 0, because if we have the three-dimensional, then z exists, but here we are considering only two-dimensional, so sz is equal to 0. So the z equation will become 0, and if you further solve these two equations, sx will become e by 1 minus v square epsilon x plus v into ey. This will be the first equation for the x plane, and for the y plane this equation will become e by 1 minus v square ey v plus epsilon x. So by measuring strain in x and y direction, the relative stress can be found out with the help of these equations. Now generally transducers are related to the measurement of longitudinal or axial strain, because all the strain can be found from it. Means we can measure all the strains with the help of transducer, but for axial strain the change in the length, means if we apply pressure to any object, so it will not expand, means you cannot see, matlab you cannot visible that the dimension of the object is expand, but that expansion is very small. So the change in the length are so small that it is difficult to measure such displacement directly. So that's why to measure this small deflections or small dimension change, we can measure with the help of strain gauge. So that's why we need to use the strain gauge, and strain gauge can be sense that minimum change in the dimension in terms of resistance change. So that's why for the measurement of strain we use generally strain gauges. Now the factors we need to be considered while measuring the strain. So generally we measure the micro strain, means as we know that it is very small, so that's why the length is in micrometer. So change in length is in micrometer, and the original length is in meter. So so from this we can see that from the original length to the change in length, the unit shows that this is the very less change in the dimension. So the to measure the strain in we can say concerned solid, now we has one has to measure the delta x and x in each direction. So generally strain magnitude is of few microstrain used in strain measurement. So that's why we apply this equation, and from the dimension you can see that the expansion of the solid or dimension change in the solid is very small, means it is in the micrometer. Now generally strains are likely to vary from point to point. Generally it is very small, that's why it is varies from the point to point. So it requires that a strain gauge must be small as possible, means we can select, or the strain gauge which we use, that must be in a small size, and the gauge length is around 5 mm. So from this length you can assume that the change in the dimension and the strain which the strain gauge which can measure the change in this change in the dimension in such small unit. So generally these two factors we need to consider while we select the strain gauge, because we have to measure the dimension changes in micrometer, and for that we cannot select the large strain gauges, because the change in the length is very small. So for that we can use small strain gauges and very sensitive strain gauges, so that it can measure and it can sense the we can say micrometer change in the length. So we need to keep in mind while we select the strain gauge, means these two points we need to consider while we select the strain gauge. Now the type of strain gauges, generally we have the different type of strain gauges. So first we'll start with the mechanical gauges. So generally this mechanical strain gauges are based on the change in length to the original length principle. So mechanical gauges generally use this principle for the measurement of strain. Now optical strain gauge, this term is related with the light. So generally they are similar to the mechanical gauge, means except that magnification is obtained with multiple reflectors using mirrors or prism, and this gauge is independent from the variation in the temperature. So temperature doesn't affect. So the measurement accuracy of this gauge is very high. So that's why we can use optical gauges where it requires, means wherever the atmosphere or surrounding condition doesn't match with any other gauges, means type of gauges, then we can use the optical gauge for, because it is independent from the temperature variation. So we can use optical gauge for the stress measurement or strain measurement. Now these are the commonly used gauges, means it is electrical gauges. So electrical gauges generally works on the principle of change in the resistance. So as we all know that the formula for the resistance related to the resistivity of the material. So as we all know that R is equal to rho L by A. So all the strain gauges, means electrical strain gauges works on that principle, means if we change the resistivity, resistance will change. If we change the length, resistivity will change, and if we change the area, resistance of that material will change. But for this kind of principle we use very sensitive material, and this sensitive material will sense the micrometer change, and so as it will shows the deflection according to the change in the dimension. Now generally the variation in the value of the resistance when the conductor is subjected to strain is more than an increase in resistance due to its dimensional change. So this property is called the piezoelectric effect. So sorry, piezoresistive effect. So change in the dimension, change in the resistance, and this effect is called the piezoresistive effect. Means piezo means some we are applying the pressure, and resistive effect means by applying the pressure the dimension of the material will change, and so as its resistance will change. That's why it is called piezoresistive effect. So it is the property of material, and we use that principle and property of material for the measurement of strain as well as the stress. Now the piezoresistive effect generally describes the change in the electrical resistivity of a semiconductor when the mechanical stress is applied. So as I explained you in the previous slide, and the resistance strain gauge are called the piezoresistive effect. So these are the types of electrical strain gauges generally we use for the strain measurement as per our requirement. So we'll start with the first type of strain gauge. First two types of the strain gauge in this lecture. The first is unbonded and second is bonded. So the first is theory of operation of resistive strain gauge and gauge factor. So before we derive the equation of gauge factor, we should know the unbonded strain gauge, means unbonded resistance wire strain gauge. So in this diagram you can see that this is the spindle, or this is the arm on which we are applying the force, and with this arm this two plates are connected with the wire, or we can say resistance wire. This is the ring on which this whole structure is mounted, and as we apply the force on this rod, the dimension of all the wires, or we can say it will get stretched, and due to the stretching of this wire its resistance will change. So we use that principle for the measurement of measurement of strain. So unbonded means what? It is floated, or it is not tied on any surface. So unbonded strain gauge generally comprises of the wire that is stretched between 2 points. So here you can see that it is stretched between 2 points, the upper one and the lower one, and or we can say it is stretched in the air. There is no any other medium, means it is not mounted on any hard surface. So the diameter of the wire is approximately, generally we use for such kind of transducer or strain gauges, is 25 micrometer, and the unbonded strain gauges are connected in bridge circuit. Suppose we connect this strain gauge in the bridge circuit. As we know that in bridge we have the balance arm. So if any of the arm get unbalanced, and galvanometer show the deflection according to the unbalancing of the arm. So suppose we connect this wire, means the strain gauge in the balanced bridge circuit. So whenever we apply the force, this cables or the wires will get stretched, and due to the stretching of this wire, according to the R is equal to rho L by A, length of the conductor will change, and as the length of the conductor will change, that balanced bridge will get unbalanced, and due to the unbalance the current starts flowing through the galvanometer, and whatever the current transferring and whatever the value indicated by the galvanometer is nothing but the force applied, and we can say we are measuring the strain in terms of electrical voltage. So this is the unbonded resistance wire strain gauge. Now this is the side view of this unbonded strain gauge wire. So here you can see that this is the fixed base, means on which we are performing this change in the length of the conductor. So this is the force we are applying over here. So if we apply the force over here, so this from this point to this point and this point to this point, this two cable will get stretched, means stretch unbonded strain gauge, both are in the air, and this two R will get compressed, means in this direction, and suppose we apply force in this direction, then the upper one will get compressed and the middle one, means this two, will get stretched. So due to the stretching of this wire, the resistance of the material will change, means the cable resistance will change. So the bridge is balanced when the no load is applied, means if there is no force or no load at that time, this conductors are in its original position, means they are not stretched. And due to this there is no free vibrations and no sag, means इसमें यहाँ पे आप देख सकते हो कि it is indicated with a straight line, and if there is force is applied, then this will get stretched, so this will become more thin, and this 2 points will have the sag like this due to the compression. So that is called the sag and vibrations. Now if the resistance of the strain gauge changes when the external load is applied, as I explained you, and this output voltage is proportional to the amount of strain applied on the strain gauge. So using this unbonded wire strain gauge, we detect the displacement up to 50 micrometer. So from this dimension, you can assume that this type of strain gauge is very much sensitive for the strain measurement. Now this is the second type of the wire strain gauge. So this is bonded resistance wire strain gauge. So this is the surface on which we mounted a wire, means this is called gauge backing, means on which we mounted the wire. Then fine wire, which is means you can, from the shape you can see that it is mounted like this, equal amount of distance between two conductor, and the shape, from the shape you can see that it is placed very uniformly. Now this is the wire grid and supporting base on which it is mounted. These two are the leads which we can connect in the balanced bridge circuit, and this is the direction of the strain applied. So the bonded resistance wire strain gauges are bonded with the cement of the surface, means the cemented surface, on the cemented surface they are bonded, and a fine wire element having the diameter of 25 micron. Generally we use the 25 micrometer cable size, and they are and it is cemented, means cemented means it is bonded, it is fixed. Now the carrier may be means generally we can use Teflon or bakelite or paper carrier as a carrier, means on which we mount the wire, and top of the wire is covered with the thin film material, so that we can provide the mechanical protection to this gauge, because if any heavy things struck on this strain gauge, then that may get that can damage the gauge wire. So due to this thin film material, we can protect this from the mechanical damage. And the resistance of the conductor is, generally we know this expression, R is equal to rho L by A. As we apply the strain, according to the strain applied, length of the conductor will change, so as the resistance will change. So rho is the specific resistance of the material. What do you mean by specific resistance? For a suppose 1 meter by 1 meter by 1 meter का अगर क्यूब अगर हम लेंगे, तो whatever the resistance offered by that material is called the specific resistance of that material. So this is the specific resistance, and L is the length of the conductor, and the A is the cross sectional area. Now the strain gauge are described in terms of its sensitivity, which is called the gauge factor. Means each and every strain gauges has its own sensitivity, and from the sensitivity we can define the gauge factor of any strain gauge. So we derive the equation for the gauge factor for this session. So it is defined as the unit change in the resistance per unit change in the length. Means as we change the length, the resistance of the material will change. And in the length of the strain gauge wire, means as length will change, resistance will change. So gauge factor generally defines the change in resistance to the original resistance and change in length to the original length ratio. So generally GF indicates the gauge factor, delta R is the change in the initial resistance, in ohms R is the resistance of the gauge wire, means whenever stress is not applied on that resistance wire, whatever the resistance offered by that wire is called the resistance of gauge wire, and whenever we apply a force, that will become delta R. Now delta L is the change in the length, and L is the length of the gauge wire, means actual length. And the equation of the strain is change in the length to the original length. So epsilon is the strain in the lateral direction, means one direction. Now from the equation 2.5.1, means from this equation gauge factor, we can write delta L by L is equal to epsilon. So it is replaced with the epsilon, delta R by R divided by epsilon. So the resistance of the conductor with uniform cross section is R is equal to rho L by A, as we know that. And the area of the wire is, we can say, the equation is pi r square. So it is replaced with the pi r square, so R is equal to rho L by pi r square. Here R is the radius, so it is d by 2, so R square will become d square by 4. So here we put this values in this equation, means R is equal to rho L by A, so R is equal to rho L by pi d square by 4. So this equation is 2.5.4, where where rho is the specific resistance, L is the length of the conductor, and D is the diameter of the conductor. Now the tension on the conductor caused the change in the length, as we already studied. So the length of the conductor increased by the factor delta L, means L was the original length, and when we apply the force, that the length will become delta L, and in turn the diameter increase by factor delta D, means the original diameter is D, so whenever we apply the force on the conductor, diameter will also change, so that will become delta D. So we can write the resistance of the conductor change equation over here. So R will become R dash. So change in length, in the previous equation we had seen that R is equal to rho L by A, so L will become L plus delta L, and A will become the pi by 4 d square was there, so pi by 4 d minus delta d square. So when you solve this equation, it will become R square is equal to rho into L plus delta L pi by 4, and this will become d square minus 2 delta d into d, and plus pi d square. So this is nothing but the mathematical expression, and where delta d is very small, hence delta square can be neglected. So if delta d is small, so delta square can we can neglect. So we are eliminating that delta d square from this equation, so this will become d square minus 2d into delta d. So this is the new equation after eliminating the delta d square. So the equation will become R dash rho L plus delta L and pi by 4 d square, and we keep common this d square from this, so 1 minus 2 delta d by d. So when we further solve this equation, will that will become rho L, we are keep it common from this L, so rho L, then this will become 1 plus delta L by L, so pi by 4 d square and 1 minus 2 pi d into d, we keep it as it is. So this will become 2.5.5 from the Poisson's ratio. As we already gone through this equation, V is equal to change in diameter to the original diameter and change in length to the original length. So here we can see this ratio. So now we are just replacing this delta d into d is equal to, if we make it subject delta d by d, then that will become V, means it is the Poisson's ratio, V into delta L by L. So just substitute this value in 2.5.5. so this R dash equation will become R dash is equal to rho L plus delta L by L, and pi by 4 d square 1 minus 2v delta L by L. So if you further solve this equation, this will become r dash rho L pi by 4 d square and into the bracket 1 plus 2v delta L by L. This is nothing but the solution of this is the mathematical expression, so you can solve it by your own way also. So delta L by L plus 2v delta L square by L square divided by 1 minus 4v square delta L square by L square. So as we know that delta is very less compared to or we can say it is less than or equal to 1, so we can neglect over here, so we are neglecting delta L term over here. So neglecting the higher power means delta L ka higher power is delta L square, so delta L square term we are neglecting from this equation. So r dash will become rho L pi by 4 d square 1 plus 2v delta L by L plus delta L by L. So delta L square term is been eliminated from this. So r dash rho L pi by 4 d square 1 plus here we keep it common 1 plus 2v, so delta L by L 1 plus 2v. Now the r dash equation will become r dash rho L pi by 4 d square. This was the repeated equation from the previous slide, so from this we are starting. So from equation number 2.5.4, so r is equal to, again we are writing the rho L by a is the pi by 4 d square, so here pi d square by r, so r dash will become r this r plus r dash, or we can say delta r. So r dash is equal to r plus delta r. We are just substituting the values, so delta r will become rho L by pi by 4 d square and delta L by L 1 plus 2v. So here delta r is equal to, this is the r, so r and delta L by L into 1 plus 2v. So just rewrite this equation, means delta r by r divide by delta L by L is equal to 1 plus 2v, but this delta r by r divided by delta L by L is the gauge factor. So here sorry, here gf is equal to this, so gf is equal to 1 plus 2v. So this is nothing but the gauge factor of a particular material. So as sensitivity change, gauge factor will change. So from the Poisson's ratio for metals lies between 2.25 and 1.35, this value you required when you calculate the example related to this equation, and gauge factor would be of the order of 1.5 to 1.7. So strain gauge having high sensitivities are required, because the dimension change whenever we apply the force is very small, so that's why higher sensitivity strain gauges are required. And if strain gauge the sensitivity is higher, then the gauge factor of the strain gauge is also higher. Now this is the difference between bonded and unbonded strain gauge that we already studied, but such kind of question can be asked in your GTU exam. So bonded strain gauge means they are bonded with the cement surface, and these are the means having they are bonded on the air, means air is the medium. So this gauge is comprised of the wire that stretched between 2 points in an insulating medium, say air is nothing but the insulating medium. And for the bonded wire gauge, that is 25 micrometer, is looped back for the fourth, means upper portion and lower portion on a base mounting plate, means upper portion of the surface, and the plate is cemented to member undergoing the stress. And for the unbonded strain gauge, the diameter of the wire is approximately 25 micrometer, and the unbounded strain gauges are generally connected in the bridge circuit. And if we connect this both in bridge circuit, we can get any change in the dimension in terms of change in the resistance, and change in the resistance we can measure in terms of voltage. So this strain gauges are very sensitive in nature, and material which we use for the strain gauge having good sensitivity, and from this we can measure a minimal change in the dimension in terms of change in the voltage. So after this topic we have the assignment question. So first two questions are assignment sorry of the worksheet questions. What do you mean by strain gauge and what is the difference between stress and strain? These two questions are the worksheet questions, and from the 3 to 3 4 and 5, these three questions are assignment questions that you need to submit at the end of the chapter. So the third question is, what is the relation between stress and strain? Explain it with suitable expression. The fourth is explain the bonded and unbonded strain gauges. And fifth is, what do you mean by the gauge factor? Explain it with suitable derivation. This question number 5 is very important from this topic, and this question is repeatedly asked in the GTU exam. So prepare it well, and all the instructions related to this assignment and worksheet question is written below the assignment question. You can take the snap of this, and if you have any further queries and doubt, so we can solve it in our doubt solving session. And also you are feel free to call me anytime, and you can WhatsApp me whenever if you find any query related to this topic. Thank you very much, student. Thank you all. Jai Swaminarayan.